Hello, my friend. Welcome, whether you've been here before or you've just found this channel tonight. This is a place where you can let go of the day and drift off to sleep while listening to calm stories about science and the universe. Tonight, we'll be exploring the quiet language of tensors and how this hidden mathematics helps explain reality itself. So settle in, close your eyes if you like, and let the words carry you softly toward rest. Chapter 1. Numbers, Arrows, and Shapes. The journey begins. When we think about mathematics, most of us begin with something very simple: numbers. They are the foundation of how humans have measured, compared, and reasoned about the world for thousands of years. At first, numbers were nothing more than marks carved into bones or clay tablets, a way of keeping track of how many animals were in a herd or how many baskets of grain were stored. These early numbers were what mathematicians call scalars, quantities that can be described with just a single value. A scalar is the most basic mathematical object. It does not carry direction, orientation, or any additional structure. Temperature is a scalar. Mass is a scalar. Time, as we usually measure it on our watches, is a scalar. Each of these can be represented by a single number, and for many centuries, this seemed sufficient for describing most of reality. But as humanity looked deeper into nature, scalars began to feel inadequate. When you describe the wind, you don't just want to know how strong it is. You also need to know which way it is blowing. That's where the next level of mathematical sophistication appears. Vectors. A vector is an arrow. It has both magnitude and direction. This seemingly small addition, giving numbers a direction, opened up an entirely new way of thinking about the universe. Instead of saying the wind is 5 meters per second, we can say it is 5 meters per second toward the north. The vector gives us orientation, and with it, a richer description of reality. Vectors were not just theoretical curiosities. They became indispensable in mechanics, physics, and geometry. Newton's laws of motion are best expressed using vectors. A ball thrown into the air has a velocity vector pointing upward, and gravity adds a force vector pointing downward. By combining them, we predict the curved path of the ball. This simple geometry of arrows became a universal tool for describing everything from planetary orbits to the flow of rivers. Yet, vectors too had their limits. Sometimes reality demanded something more subtle. Imagine describing how a solid object deforms when you press on it. At every point in the material, the forces might be pushing, pulling, or twisting in different directions. A single arrow cannot capture all that information. Engineers needed a way to describe stresses acting in multiple directions at once, and how those stresses caused strains. Here enters the idea of matrices, arrays of numbers that could capture interactions in more than one direction. A matrix can describe how a vector changes when it is rotated, stretched, or compressed. With matrices, mathematics gained the ability to capture linear transformations, the rules by which shapes and arrows change inside space. For a while, matrices seemed to complete the picture. But the universe is not always linear, and it is not always simple. As scientists began thinking about forces in curved surfaces, about the geometry of the Earth, or about electromagnetic fields extending through space, even matrices were not enough. There needed to be a general framework, something that could describe quantities of any rank, quantities that might involve not just numbers or arrows, but entire rules for how arrows and shapes change when they move through space, that itself might be curved. That is when tensors entered the story. But before we can grasp tensors, we need to understand the stepping stones more carefully. Consider again the scalar. A scalar does not change when we rotate our coordinate system. If you say the temperature outside is 20 degrees Celsius, it does not matter whether you are facing north or south, or whether you describe your coordinates in meters or feet. The scalar remains the same. It is an invariant. This invariance is important because physics demands descriptions that do not depend on who is doing the measuring or which orientation they use. Vectors are slightly more subtle. If you describe a velocity vector in one coordinate system and then rotate your axes, the components of the vector change. What was once moving 3 units in the x direction and 4 units in the y direction might become 5 units in some diagonal direction after you rotate your view. Yet the underlying arrow, the geometric object, remains the same. This is the first time we encounter the idea of transformation rules. The components of a vector may change, but they change in a predictable way so that the vector itself remains a consistent description of reality. Matrices brought even more structure. They are not just arrows, but instructions. A matrix can take a vector and rotate it, stretch it, or flip it. In physics, the inertia of an object is not always the same in all directions. A spinning top resists being moved differently depending on the axis along which you push it. This resistance can be captured by what is called an inertia tensor, which, in simple cases, can be represented by a matrix. Here, again, we see the expansion of descriptive power, from numbers to arrows to transformations of arrows. At this stage, the story of mathematics and physics was already rich. Scalars, vectors, and matrices were enough for Newtonian mechanics, enough for much of engineering, and enough to describe countless everyday phenomena. But the deeper humanity looked into the universe, the more it became clear that something more universal was needed. To grasp why, imagine living on the surface of a sphere. On such a curved surface, the familiar rules of Euclidean geometry begin to break down. The shortest path between 2 points is not a straight line, but a great circle. The sum of the angles of a triangle is not always 180 degrees. The geometry bends with the surface. How do we describe such a space in a way that remains valid no matter where we stand or how we rotate our perspective? The answer lies in tensors. Tensors generalize all the concepts we have encountered so far. They include scalars, vectors, and matrices as special cases. But they go further, providing a single framework for describing how quantities behave when the underlying space is not simple and flat, but can twist and curve. A tensor is an object that transforms in a consistent way when we change coordinates, ensuring that physical laws remain the same for all observers. This consistency, this invariance, is the true heartbeat of physics. The journey from scalars to tensors mirrors the journey of human understanding. We began with simple numbers, counting our world. Then we discovered direction, arrows pointing through space. Then we found matrices, rules for shaping arrows. Finally, we arrived at tensors, a universal grammar capable of describing reality in its full depth. Each step came not from abstraction for its own sake, but from necessity. As the problems we faced grew more complex, from predicting planetary orbits to describing curved spacetime, mathematics had to evolve. This chapter is only the beginning, and we will go much deeper. But even at this stage, we can sense the elegance of the structure. Scalars are like single notes. Vectors are like melodies, giving direction and movement. Matrices and tensors are like harmonies, weaving together many notes into something richer, something capable of describing entire symphonies of interaction. The language of tensors is the symphony of reality itself. And here lies a quiet existential thought. At the deepest level, reality seems to demand to be written in this language. It is not that we force tensors onto the universe, but rather that the universe revealed itself through them. Numbers, arrows, and shapes are not just inventions of the human mind. They are echoes of the order that underlies existence. When you think of a tensor, you are not just thinking about math. You are touching the hidden grammar of the cosmos, a grammar that whispers to us that reality is structured, interconnected, and profoundly elegant. Chapter 2. What exactly is a tensor? The word tensor carries a kind of mystery. It is used in physics, engineering, mathematics, and even computer science, yet for many people, it feels like an impenetrable concept. Some might imagine it as just a higher dimensional matrix, while others think of it as a technical tool for Einstein's theory of relativity. Both impressions hold fragments of truth, but neither captures the full essence. To understand what a tensor is, we must step back and consider why such a concept exists at all. The heart of the matter lies in describing physical reality in a way that does not depend on the viewpoint of the observer. Nature does not change its rules because you decide to rotate your coordinate system or to measure distances in feet rather than meters. But the numbers we assign to objects, the coordinates, the components of a velocity, or the entries of a matrix, do change. They change depending on how we choose to describe the situation. A tensor is a mathematical object designed to live independently of these choices, while still providing the transformation rules that link one description to another. At its most basic, a tensor is a collection of numbers that behave in a particular way under a change of coordinates. The emphasis is not on the numbers themselves, but on how they transform. Consider standing at a busy intersection, describing the velocity of a car. If you align your x-axis eastward and your y-axis northward, the car's velocity might be 3 units in the x direction and 4 in the y direction. But if someone else tilts their axes 45 degrees, their numbers will differ, perhaps 5 units along their new x-axis and 2 along their new y-axis. Both observers are describing the same physical reality. The underlying velocity is one object, but it takes on different component values depending on the coordinate system. This object is a vector, which is the simplest non-trivial example of a tensor. Tensors generalize this idea. Just as vectors transform in a predictable way when coordinates are changed, tensors of higher rank transform according to more intricate but equally consistent rules. The elegance lies in this consistency. No matter how we rotate, tilt, or reshape our viewpoint, the tensor encodes reality in such a way that its meaning is preserved. The word rank often appears when describing tensors. The rank of a tensor refers to how many directions or indices it involves. A scalar is rank 0. It has no direction and no indices, just a number that remains invariant under all transformations. A vector is rank 1. It requires one index to specify its components, such as velocity in the x direction or y direction. A matrix can be thought of as rank 2, needing 2 indices, such as force in one direction acting along another direction. Higher rank tensors extend this logic, involving 3, 4, or more indices, allowing them to capture relationships among multiple directions at once. While this description may sound abstract, tensors appear naturally in the fabric of physics. The stress inside a material, for example, is not just about how much force is applied. It also matters in which direction the force acts and along which surface it acts. The stress tensor is a rank 2 tensor, neatly capturing all of these combinations at every point in the material. In electromagnetism, the electromagnetic field is described not simply by electric and magnetic vectors, but by a unified field tensor, which brings together the two phenomena into a consistent mathematical form. In general relativity, Einstein's equations relate the curvature of spacetime, represented by one tensor, to the distribution of energy and momentum, represented by another tensor. Without the tensor framework, these relationships would be impossible to write in a way that holds true for all observers. But to really understand what a tensor is, one must appreciate its geometric meaning. Imagine again being on the surface of a sphere. If you move north, then east, then south, you may not end up exactly where you started because the surface is curved. The rules of geometry are different on curved spaces. A tensor provides a way to describe these rules at every point. It tells you how distances are measured, how angles are preserved or altered, and how arrows shift as they move across the surface. In this sense, tensors are not just arrays of numbers. They are the machinery that encodes the geometry and physical laws of the world, point by point. It is important to note that a tensor is not tied to any particular coordinate system. When we write down its components, we are merely choosing a language, a local perspective, but the tensor itself exists beyond that choice. This distinction is subtle but essential. Many misunderstandings come from thinking of a tensor as merely a table of numbers. It is better thought of as an object that can be represented in many ways, depending on perspective, yet remains fundamentally the same. The mathematics of tensors allows us to describe how these objects change when we alter our coordinates. The transformation rules are precise, ensuring that physical laws written in tensor form remain valid for all observers. This universality is why tensors became indispensable to modern physics. They provided Einstein the language to express how space-time bends under the influence of mass and energy. They allow engineers to design aircraft wings that can withstand stress from multiple directions. They enable computer scientists to construct neural networks capable of recognizing faces and voices. An analogy can help bring clarity. Think of a novel written in different languages. The words change from English to French to Japanese, but the story remains the same. The tensor is like the story, while the specific components in a coordinate system are like the words in a particular language. Changing coordinates is like translating. As long as the rules of translation are followed, the meaning, the physical reality, remains intact. Another way to think of tensors is as maps between vectors. A vector can be considered an input, and a tensor tells you how that input transforms into an output. For example, in mechanics, applying a force vector to an object results in an acceleration vector. The proportionality between them depends on the mass, which can be described in some cases by a tensor. The tensor serves as the link, the mediator between different kinds of vectors, ensuring that the relationship is consistent in all coordinate systems. We can also consider tensors as geometric fields spread across space and time. At every point in the universe, there may be quantities that vary with direction, curvature, or interaction. The metric tensor in general relativity is one such field, existing at every point in spacetime, telling particles and light how to move along their paths. This tensor does not merely describe physical reality. In a very real sense, it defines it. Without it, there is no geometry, no distances, no time intervals. The metric tensor is the stage upon which the universe unfolds. The abstraction of tensors might feel daunting, but it is precisely this abstraction that makes them powerful. They are not tied to one problem or one branch of science. They are a universal framework, appearing wherever relationships must be preserved across different perspectives, whether in the bending of space-time, the flow of fluids, the deformation of solids, or the training of artificial intelligence models. Tensors quietly carry the weight of description. At this point, one might ask, are tensors simply human inventions, or do they reflect something fundamental about the universe itself? The cautious scientific answer is that tensors are tools constructed by mathematicians, refined by physicists, and applied across disciplines. But there is another perspective, one that many great scientists have hinted at. Perhaps mathematics is not just our invention, but a discovery of patterns that exist independently of us. Tensors, in this view, are not arbitrary constructs. They are part of the hidden grammar of nature, waiting to be uncovered. It is striking to realize that while most of us never think about tensors in daily life, we are surrounded by them constantly. The stresses in the walls of our homes, the electromagnetic fields carrying our Wi-Fi signals, the very curvature of space-time that keeps the Earth orbiting the Sun, all are described by tensors. They are the unseen framework that sustains reality, invisible but essential. And here, in the quiet reflection at the end of this chapter, lies something almost existential. When you touch the idea of a tensor, you are reaching beyond mere numbers and equations. You are glimpsing the structures that underlie existence itself. The world is not chaos. It is patterned, structured, and describable. Tensors are the mathematical embodiment of that truth. They remind us that reality, however vast and mysterious, is bound together by consistency and harmony. Chapter 3. From Flat Maps to Curved Worlds. For much of human history, geometry was thought to be the study of flatness. Euclid, working in Alexandria more than 2,000 years ago, codified the rules that seemed obvious to anyone drawing lines in the sand or marking shapes on papyrus. His system, later called Euclidean geometry, was built on simple postulates. A straight line can be drawn between any 2 points. Parallel lines never meet. The angles of a triangle always sum to 180 degrees. These rules matched our intuition, and they matched the landscapes where human life unfolded. Fields, walls, and roads that could be approximated as flat. For centuries, no one seriously questioned whether these principles were universal. But the Earth itself posed a quiet contradiction. Sailors navigating across oceans noticed that parallel lines, such as lines of longitude, did meet at the poles. The angles of a large triangle drawn on the surface of the globe, connecting, say, the equator and 2 meridians, added up to more than 180 degrees. The surface of the Earth was not flat, and its geometry was not Euclidean. At first, this was seen as an exception, a complication to be ignored when drawing maps. The maps themselves, after all, were always drawn on flat sheets of paper, and they distorted distances and shapes in order to do so. But the distortions were tolerated as practical necessities, not as fundamental truths. The real shift began when mathematicians started asking whether geometry itself could be generalized. What if Euclid's postulates were not the only possibility? Could there be other consistent systems of geometry in which parallel lines behaved differently, or the sum of a triangle's angles varied? The 19th century brought bold answers. Carl Friedrich Gauss, one of the greatest mathematicians of all time, quietly developed methods for measuring the curvature of surfaces. He showed that the curvature of a surface is intrinsic, meaning it can be detected entirely from within the surface, without reference to the surrounding space. A two-dimensional being living on the surface of a sphere could, by measuring triangles and distances, discover that it lived in a curved world, even without ever seeing the sphere from outside. This was a profound revelation. Geometry was not about flatness. It was about the properties of space itself, whether flat or curved. Gauss's student, Bernhard Riemann, extended these ideas in his groundbreaking 1854 lecture on the hypotheses which lie at the foundations of geometry. Riemann proposed that geometry should be understood in terms of manifolds, spaces that might look flat when viewed locally but could be curved globally. A manifold is like a patchwork of flat maps stitched together to cover a curved surface. Each map works well in its local neighborhood, but no single flat map can cover the whole space without distortion. This was a leap into abstraction, but it was necessary. Riemann realized that the geometry of space could be described by a mathematical object that told you how to measure distances and angles at every point. That object, though Riemann did not yet use the term, was a tensor, specifically the metric tensor. The distinction between flat and curved worlds becomes especially clear when we compare how lines behave. In Euclidean space, the shortest distance between 2 points is a straight line. On a sphere, the shortest distance is not a line at all, but a great circle, such as the path airplanes follow across continents. In curved spaces, the concept of a straight line is replaced by the concept of a geodesic. A geodesic is the generalization of straightness, the path that locally minimizes distance. In flat maps, geodesics are lines. On a sphere, geodesics are arcs of great circles. In more complex spaces, geodesics may bend and twist in ways that defy our intuition, but they are always determined by the geometry of the space. The tools of Euclidean geometry proved insufficient to handle these curved worlds. Parallel postulates, which seemed self-evident, turned out to be conditional. In positively curved spaces like spheres, parallel lines tend to converge. In negatively curved spaces, such as hyperbolic geometry, parallel lines diverge. These were not paradoxes or errors, but natural consequences of living in geometries different from the flat plane. The universe, it turned out, did not need to conform to human intuition. Instead, human intuition had to expand to encompass new forms of space. Curved geometry is not merely an abstract curiosity. It describes real physical situations. The Earth is a curved surface. Light traveling across vast cosmic distances bends in the presence of massive objects. Even the trajectories of planets are more accurately described not as ellipses in flat space, but as geodesics in the curved geometry created by the sun's mass. Einstein's general theory of relativity formalized this connection, showing that spacetime itself is a four-dimensional curved manifold. But long before Einstein, the groundwork was laid by mathematicians like Riemann, who gave us the language to describe spaces that defy flatness. One of Riemann's most remarkable insights was that curvature itself can be quantified and encoded. Curvature is not just a vague bending, but a precise mathematical property. For a two-dimensional surface, it can be described at each point as either positive, negative, or zero, corresponding to spherical, hyperbolic, or flat geometry. In higher dimensions, curvature becomes more complex, requiring the use of tensors to capture it. The Riemann curvature tensor is the object that encapsulates how much and in what way a space is curved. It tells us how vectors change as they are transported around loops in space, and whether they return to their original orientation or not. In flat space, they always return unchanged. In curved space, they may twist, rotate, or alter, revealing the presence of curvature. The leap from flat maps to curved worlds also changes how we think about measurement itself. On a flat plane, distance can be measured with the familiar Pythagorean theorem. The square of the hypotenuse equals the sum of the squares of the legs. But in curved geometry, the formula for distance depends on the shape of space. The metric tensor provides the rule for calculating distances and angles, adapting to the local geometry at every point. In this way, the metric tensor generalizes the Pythagorean theorem to any curved manifold, from the surface of a sphere to the fabric of spacetime. It is tempting to think of curvature as something external, like bending a sheet of paper in three-dimensional space. But Riemann's genius was to show that curvature can be intrinsic. You do not need to imagine an embedding space. The geometry is entirely contained within the manifold itself. A being confined to the surface can measure the curvature without ever leaving it. This idea is critical for physics because we cannot step outside the universe to view it from above. We can only measure from within, using the tools of intrinsic geometry. The transition from flat to curved thinking is one of the deepest conceptual shifts in science. It replaces certainty with flexibility, showing that even the most obvious truths of geometry are not universal, but contingent. It also introduces a new vision of reality, one where space and geometry are not passive stages upon which events occur, but active participants that shape and are shaped by the contents of the universe. In practical terms, curved geometry has found countless applications. In navigation, understanding the Earth as a sphere allows accurate calculation of distances, flight paths, and satellite orbits. In cartography, the struggle to represent the curved surface of the Earth on flat maps has produced many projections, each with its distortions, reminding us that no flat map can fully capture a curved world. In architecture and engineering, curved surfaces such as domes and arches gain strength from their geometry, a strength that arises directly from non-Euclidean principles. And in physics, curved geometry is the stage upon which the drama of relativity unfolds, determining the motion of stars, galaxies, and light itself. As we extend our gaze further into cosmology, the curvature of space becomes a question of ultimate significance. Is the universe flat, spherical, or hyperbolic? Each possibility carries implications for its fate. A flat universe may expand forever at a critical balance. A positively curved universe could one day collapse back upon itself. A negatively curved universe may expand endlessly, spreading galaxies into an ever-thinning cosmos. These are not abstract possibilities, but real questions addressed by measurements of cosmic background radiation, galaxy distributions, and gravitational lensing. The shape of the universe is, in essence, a question of geometry. Tensors, though not yet discussed in detail in this chapter, will become indispensable in formalizing all of this. They provide the grammar by which curvature is expressed, the precise rules that allow us to calculate how much deviation from flatness exists at each point. Without them, curved geometry would remain an intuitive idea, useful for sailors and architects, but insufficient for physicists probing the deepest laws of the cosmos. And here, as this chapter closes, comes the quiet existential reflection. Flat maps are comforting, simple, and easy to hold in our hands. But they are only approximations, shadows of a deeper truth. The world itself is curved, both literally in the surfaces we walk upon and figuratively in the cosmos that expands around us. To learn to see beyond the flat is to accept that reality is richer, stranger, and more complex than first appearances suggest. And yet in that complexity lies beauty, a universe that bends, twists, and curves, but remains comprehensible to minds willing to follow its paths. Chapter 4. The Italian mathematicians who gave Einstein his language. In the story of modern physics, Albert Einstein often stands as the central figure, the genius who redefined space, time, and gravity. His name has become synonymous with intellectual brilliance, and the theory of general relativity is often described as his crowning achievement. Yet, behind the elegance of his equations lies a mathematical language he did not invent. That language was the creation of two Italian mathematicians, Gregorio Ricci Curbastro and his student Tullio Levi-Civita, whose work in the late 19th and early 20th centuries provided the indispensable tools Einstein needed to describe a curved universe. Without their development of tensor calculus, general relativity could never have been expressed. Ricci Curbastro was born in 1853 in Lugo, a small town in northern Italy. He studied mathematics in Rome and then in Pisa, where he worked under Enrico Betti, an influential mathematician who had introduced the ideas of Riemannian geometry into Italian mathematics. Ricci became fascinated by the problem of describing geometry in ways that did not depend on the choice of coordinates. At the time, geometry was still often tied to specific representations, coordinates, formulas, and calculations that worked locally but did not always translate globally. Ricci wanted something more universal, a calculus that could be applied in any situation, regardless of the coordinate system chosen. His answer was what he called the absolute differential calculus. The term may sound forbidding, but the idea was profoundly elegant. Create a system of rules for differentiating and manipulating quantities that remain valid no matter how one rotates, distorts, or redefines the underlying coordinate grid. This was the beginning of tensor calculus. Ricci's work extended Riemann's earlier insights into curved geometry. Riemann had shown that manifolds could have intrinsic curvature, and that this curvature could be measured internally. But to make these concepts practical for computation, a more systematic language was required. Ricci provided that language, developing the rules for how tensors behave under differentiation, how they transform under coordinate changes, and how they can be combined to describe curvature and geometry in a consistent way. Yet, Ricci's work remained largely a mathematical curiosity. He published his results in 1887 and 1892, refining them over the years, but the physics community did not yet see a pressing need for such abstraction. The methods seemed far removed from the concrete concerns of mechanics or electromagnetism. Ricci himself may not have realized how far-reaching his ideas would become. It was his student, Tullio Levi-Civita, who deepened the theory and made it more accessible. Levi-Civita, born in Padua in 1873, quickly distinguished himself as a mathematician of exceptional clarity and rigor. He collaborated closely with Ricci, helping to produce the monumental 1900 paper, Méthode de calcul différentiel absolu et leurs applications, which presented tensor calculus in full form. This paper, published in the Mathematische Annalen, was not widely read outside of mathematical circles. Its content was dense, and its style was highly formal. Yet it laid out with precision the framework that would later allow Einstein to express the fundamental laws of gravity in a way that transcended coordinate systems. In it were the concepts of covariant and contravariant components, the rules of contraction and index manipulation, and the formulas for curvature tensors that would eventually appear in Einstein's field equations. When Einstein began searching for a new theory of gravity around 1907, he quickly realized that Newton's laws, which treated gravity as a force acting instantaneously across space, were incompatible with his special theory of relativity, which insisted that nothing can travel faster than light. he intuited that gravity must be geometry, that mass and energy somehow shape the fabric of spacetime, and that objects move not because they are pulled by invisible forces, but because they follow the natural curves of that fabric. But intuition was not enough. To turn these ideas into equations, Einstein needed a mathematical language capable of describing curved four-dimensional spacetime. At first, Einstein tried to work with the tools he already knew: calculus and differential equations in relatively simple forms. But he quickly ran into difficulties. The mathematics of curved surfaces was notoriously complicated, and Einstein struggled to find the right formalism. In 1912, his friend and mathematician Marcel Grossmann suggested he look into the work of Ricci and Levi-Civita. Grossmann, more familiar with the literature, recognized that tensor calculus was precisely the tool Einstein required. Einstein later admitted that when he first encountered Ricci and Levi-Civita's paper, he found it almost incomprehensible. The notation was unfamiliar, the concepts abstract, and the calculations intricate. But he also realized that within this framework lay the key to unlocking his theory. Over the next 3 years, he immersed himself in tensor calculus, working alongside Grossmann, and later corresponding with Levi-Civita himself. In fact, in 1915, as Einstein was refining his field equations, Levi-Civita wrote him letters clarifying aspects of the mathematics, offering guidance that proved essential. The collaboration between physicists and mathematicians was not just incidental, it was transformative. Einstein provided the physical intuition, the conviction that gravity was geometry, while Ricci and Levi-Civita provided the language to make that intuition precise. The Einstein field equations, published in November 1915, are tensor equations. They relate the Einstein tensor, which encodes the curvature of spacetime, to the stress-energy tensor, which encodes the distribution of mass and energy. The form of these equations guarantees that the laws of gravity are the same for all observers, regardless of their coordinate system or perspective. This universality, this independence from arbitrary choices, was only possible because of the framework Ricci and Levi-Civita had created. It is sometimes said that Einstein's genius was as much about recognizing the right tools as about inventing new theories. In this case, his genius lay in seeing that tensor calculus, developed decades earlier in relative obscurity, was the perfect fit for his revolutionary vision of gravity. Ricci and Levi-Civita did not set out to reinvent physics. They set out to generalize geometry. But by doing so, they unknowingly armed physics with the language of the cosmos. Levi-Civita's role in the history of relativity is particularly poignant. He and Einstein exchanged letters in which Levi-Civita offered encouragement and clarification, helping Einstein through technical challenges. Later in life, Levi-Civita continued to contribute to mathematics, but his career was tragically disrupted by the fascist racial laws in Italy, which targeted Jews and stripped him of his university position. Despite these hardships, his work lived on, embedded in the very structure of modern physics. Ricci, meanwhile, remained less well known outside of mathematical circles. He died in 1925. 10 years after Einstein presented his field equations, perhaps unaware of just how central his ideas had become to our understanding of the universe. In modern textbooks, the names of Ricci and Levi-Civita appear frequently in the notation: Ricci tensors, Levi-Civita connections, Ricci curvature. These are not just honorary mentions, but living parts of the mathematics used every day by physicists and engineers. The Italian contribution to Einstein's theory is a reminder that scientific revolutions are rarely the work of a single mind. They are collaborations across time and disciplines, the weaving together of insights that may have seemed isolated at first, but converge in moments of profound transformation. Einstein's relativity is one of the most celebrated achievements of the 20th century, but it rests on the foundation built by Ricci and Levi-Civita. Without their calculus, relativity would have remained an inspired but vague idea, lacking the mathematical structure to describe reality with precision. Today, tensor calculus is not confined to general relativity. It appears in continuum mechanics, in fluid dynamics, in electromagnetism, and in modern computer science, where frameworks such as TensorFlow take their very name from the concept. This broad applicability underscores just how powerful Ricci and Levi-Civita's framework turned out to be. What began as an abstract mathematical exercise became one of the most versatile tools in all of science. There is something profoundly humbling in this history. Two mathematicians working in relative obscurity, motivated by pure curiosity, created a language that would later allow Einstein to change our understanding of reality. It reminds us that progress often depends not on immediate application, but on the patient cultivation of ideas, waiting for the right moment to reveal their power. And here's where the existential reflection belongs. The universe speaks a language that is not bound by culture, nationality, or time. Ricci and Levi-Civita did not invent that language. They uncovered a grammar that was always there, hidden in the folds of geometry itself. Einstein merely learned to use it. To study this history is to glimpse a deeper truth, that reality can be described, that human minds across generations can collaborate silently through mathematics, and that in the quiet work of abstraction lies the power to change how we see the cosmos. Chapter 5. Einstein's field equations. Matter tells space how to curve. By the autumn of 1915, Albert Einstein stood on the brink of completing one of the greatest intellectual achievements in human history. He had spent years searching for a theory that would unite his insight from special relativity with a new understanding of gravity. Newton had described gravity as a force acting at a distance, instantaneous and universal. But this clashed with relativity, which declared that no influence can travel faster than light. Einstein believed that the answer lay not in forces acting across empty space, but in space and time themselves. If geometry could be dynamic, bending in response to matter and energy, then gravity would no longer be a mysterious invisible pull. It would be the manifestation of curved spacetime. The challenge was to express this profound idea in precise mathematical terms. Geometry, after all, is not simply a metaphor. It is a measurable structure, and to describe its bending requires a formal language. Thanks to Ricci Curbastro and Levi-Civita, Einstein had at his disposal the calculus of tensors, the machinery capable of encoding curvature in any dimension. Over 3 years of intense effort, Einstein struggled with the technical details, refining and discarding versions of his theory, until in November 1915 he stood before the Prussian Academy of Sciences in Berlin and presented the final form of his equations. The Einstein field equations are compact in notation, yet vast in implication. They state, in essence, that the geometry of space-time is determined by the matter and energy within it. The phrase Einstein himself used was poetic. Matter tells space how to curve, and space tells matter how to move. In other words, the distribution of mass and energy shapes the geometry, and that geometry dictates the paths of particles and light. It is a self-consistent system where matter and geometry are inseparably linked. What makes these equations revolutionary is their universality. In Newtonian physics, gravity was a force vector pointing from one mass to another, its strength falling off with the square of the distance. It worked beautifully for many practical calculations, from predicting eclipses to guiding ships at sea. But it was not absolute. It depended on the assumption of a fixed flat stage on which masses moved. Einstein's equations, by contrast, apply to any situation in any coordinate system across the entirety of spacetime. They are covariant, meaning their form is the same for all observers. This was the realization that gravity was not just another force, but the very structure of the cosmos. The core of the equations links two tensors. On one side is the Einstein tensor, a mathematical object built from the curvature of spacetime. This tensor condenses the information of how spacetime bends, stretches, and twists. On the other side is the stress-energy tensor, which contains the energy, momentum, pressure, and stress of whatever matter and fields are present. The equality of these two tensors is the statement that geometry and matter are in balance. The universe is a dialogue between what fills it and the shape it takes. Though compact in symbolic form, the equations are highly nonlinear and difficult to solve. Unlike many physical systems, where equations can be solved step by step, the Einstein equations tie everything together. The curvature at one point depends on the distribution of matter everywhere else, and the distribution of matter responds to the curvature in return. This complexity makes exact solutions rare, but the ones we have are striking. The simplest case is empty space, where the stress-energy tensor vanishes. In this case, the field equations reduce to a statement about the curvature itself. Karl Schwarzschild, a German physicist serving on the Eastern Front during World War I, found the first exact solution to Einstein's equations in 1916. His solution described the geometry of spacetime around a spherical mass. It was within this solution that the concept of a black hole was born, though it would take decades for physicists to fully appreciate it. Other solutions soon followed. The Friedmann-Lemaitre models, developed in the 1920s, showed that Einstein's equations naturally allowed for an expanding or contracting universe, a discovery that revolutionized cosmology. Instead of being eternal and static, the universe was dynamic, its fabric stretching over time. Observational evidence, beginning with Edwin Hubble's discovery of galactic redshifts, confirmed this prediction, establishing the expanding universe as one of the most important consequences of Einstein's theory. What is remarkable is how such diverse phenomena all flow from the same set of equations. The orbit of Mercury, which stubbornly resisted Newtonian explanations, is perfectly accounted for by Einstein's curvature. Light bending around the Sun, first measured during the 1919 solar eclipse, is another direct consequence. The existence of gravitational waves, ripples in spacetime produced by massive accelerating objects, was predicted by Einstein in 1916 and directly observed a century later in 2015 by the LIGO collaboration. Each of these discoveries confirmed that the field equations are not just elegant mathematics, but faithful descriptions of reality. To appreciate their depth, it helps to reflect on what the equations represent conceptually. They are not simply instructions for calculating trajectories or predicting outcomes. They are a blueprint for reality itself. The Einstein tensor encodes the shape of spacetime, while the stress-energy tensor encodes the contents of the universe. To equate them is to say that geometry and matter are not separate realms, but two sides of the same coin. Space is not a void. It is a participant in the cosmic dance. Matter is not an isolated actor. It is a shaper of the very stage upon which it moves. This insight blurs the boundary between physics and philosophy. In the Newtonian worldview, space was absolute, a rigid background that existed independently of what occurred within it. Einstein's equations shattered that view. Space and time are dynamic, malleable, and responsive. They are woven together into space-time, and this fabric bends under the influence of matter and energy. The image of the universe is no longer that of actors on a fixed stage, but of a stage that shifts, warps, and flows with the play itself. From a practical standpoint, the equations have become the foundation for modern astrophysics and cosmology. They are used to model the life cycles of stars, the dynamics of galaxies, the evolution of the universe as a whole. They are embedded in simulations of gravitational waves, in the design of GPS systems that must account for relativistic time shifts, and in our understanding of exotic objects like neutron stars and black holes. The predictive power of the equations has been tested again and again, and each time they have held true, guiding us into deeper and stranger territory. Yet, as successful as they are, Einstein's field equations are not the final word. They do not incorporate quantum mechanics, the other great pillar of 20th century physics. At very small scales, the smooth fabric of spacetime described by the equations is expected to give way to quantum fluctuations, where geometry itself becomes uncertain. Reconciling general relativity with quantum theory remains one of the central challenges of modern physics. String theory, loop quantum gravity, and other approaches all attempt to extend or replace Einstein's equations, but so far none has achieved universal acceptance. For now, the field equations remain the most accurate description we have of gravity, though physicists know they are incomplete. It is worth pausing to consider the beauty of the equations despite their complexity. They embody a profound simplicity. Geometry equals matter. That single statement links the two most fundamental aspects of our experience, space and substance, into a unified whole. They remind us that the universe is not arbitrary but structured, governed by principles that are consistent, elegant, and comprehensible. And at the end of this reflection, the existential note emerges quietly. To write down Einstein's field equations is to glimpse the architecture of reality. These are not just symbols on paper. They are the very rules by which stars burn, galaxies collide, and the cosmos expands. They are the conversation between matter and space, whispered across the void. For a brief moment in understanding them, we step outside our small perspective and recognize that the same laws shaping the farthest galaxies also cradle us here, on this small world circling an ordinary star. Chapter 6: Tensors in Motion. Describing forces and fields. When Einstein completed his field equations, the tensor became more than a mathematical curiosity. It became the essential language of physics. But general relativity is not the only arena where tensors operate. They are the natural language of forces and fields across science, providing a way to describe not only the geometry of space-time, but also the interactions that play out within it. To understand how, we must step into the dynamic world of fields, invisible structures that permeate space and time, carrying forces, storing energy, and governing motion. In classical mechanics, forces were first conceived as vectors. Newton's second law expressed this clearly. Force equals mass times acceleration, a relationship captured neatly by arrows pointing in directions of motion. Vectors were sufficient to describe the simple push and pull of bodies in flat space. But the universe proved more complicated. As physicists explored electricity, magnetism, and the mechanics of continuous media, it became clear that a single vector was not always enough. forces could act differently depending on orientation, pressure could vary in different directions, and stresses could combine in intricate ways. What was needed was a framework that went beyond vectors, a framework capable of encoding the richness of these interactions. That framework was the tensor. Consider the stress tensor in continuum mechanics. Imagine a solid block of material. At every point within it, forces can act along multiple surfaces and in multiple directions. If you push on the top of the block, stresses develop not only vertically but also laterally as the material responds to compression. A vector could never capture all these simultaneous interactions. A tensor, however, can. The stress tensor assigns to each direction a vector of forces acting on a surface oriented that way. In essence, it provides a complete local description of how the material experiences internal forces. With it, engineers can predict how bridges bear weight, how aircraft wings withstand turbulence, and how tectonic plates build up pressure before earthquakes. In fluid dynamics, tensors are equally indispensable. A flowing liquid does not exert uniform forces in all directions. Shear stresses, viscosity, and pressure all act differently depending on orientation and velocity. The stress tensor again encodes these complexities, allowing physicists to derive the equations of fluid motion with remarkable accuracy. Weather systems, ocean currents, and even blood circulation in the human body are all governed by these tensorial descriptions. Perhaps the most elegant example of tensors in motion is found in electromagnetism. James Clerk Maxwell's equations unified electricity and magnetism in the 19th century, showing that oscillations in these fields propagate as waves at the speed of light. In their original form, Maxwell's equations were a set of 4 vector equations, already revolutionary. But when expressed in tensor form, their beauty and symmetry become even clearer. The electromagnetic field can be represented as a rank 2 tensor, the electromagnetic field tensor, which packages the electric and magnetic components into a single object. This tensor makes explicit the unity of electricity and magnetism. What appears as an electric field in one frame of reference may appear partly as a magnetic field in another. The tensor ensures the laws of electromagnetism hold true across all frames, revealing that electricity and magnetism are not separate phenomena, but 2 aspects of one underlying field. In relativistic contexts, this unification becomes especially important. A moving charge produces both electric and magnetic effects, depending on the observer's perspective. The tensor formulation guarantees consistency, preserving the covariance of Maxwell's equations under Lorentz transformations. In this way, tensors safeguard the universality of the laws, no matter how the observer moves. The electromagnetic field tensor also provides a natural way to express the stress energy carried by fields themselves, not only by matter. Light, though massless, carries energy and momentum, and this too must be accounted for in the balance of the universe. Tensors also appear in elasticity theory, where they describe how materials deform under applied forces. The strain tensor, for example, quantifies how distances and angles change within a material as it stretches or compresses. This tensor is closely related to the stress tensor, and together they embody Hooke's law in a general form. Stress is proportional to strain. From skyscrapers to spacecraft, the design of structures depends critically on understanding these tensorial relationships. Without them, engineering would be reduced to trial and error, a dangerous gamble in a world where failure can cost lives. The ubiquity of tensors in describing forces and fields reveals their true nature. They are not confined to one theory or one domain of physics. Rather, They are the general framework for encoding how quantities interact across directions and perspectives. Whether the system is a crystal lattice under pressure, a fluid flowing through a pipe, or a star radiating electromagnetic waves, tensors provide the complete local description. Even more profoundly, tensors show that forces and fields are not separate from geometry, but entwined with it. In general relativity, the stress-energy tensor does not merely describe matter and fields as independent actors. It couples them to spacetime itself. Electromagnetic fields, for instance, contribute to curvature just as mass does. Radiation and pressure have gravitational effects, and all of this is captured by the stress-energy tensor. In this sense, tensors in motion are not just mathematical conveniences. They are the language in which matter, fields, and geometry communicate. Modern physics has extended these insights into the quantum realm. In quantum field theory, the fundamental entities are not particles, but fields that span all of space and time. Each type of particle corresponds to excitations of an underlying field, and these fields are often represented by tensor quantities. Gauge fields, which govern the interactions among particles, are described by tensors that ensure consistency with the principles of symmetry and invariance. For example, the gluon field in quantum chromodynamics, which binds quarks together inside protons and neutrons, is represented by a tensor field obeying precise transformation laws. The connection between tensors and symmetry is not accidental. Symmetries lie at the heart of physics, and tensors are the mathematical objects that respect them. When a system has rotational symmetry, for instance, tensors provide the natural language to express how quantities transform under rotations. When the symmetry is more abstract, such as the internal symmetries of particle physics, tensors still provide the scaffolding. They ensure that physical laws retain their form across transformations, preserving the unity of the theory. Another striking arena where tensors in motion appear is in plasma physics and astrophysics. Plasmas, which make up most of the visible universe, are governed by a combination of electromagnetic and fluid dynamic forces. Their behavior is captured by magnetohydrodynamics, a field that relies heavily on tensor equations to couple magnetic fields, pressure, and flows. Without tensors, it would be impossible to simulate the dynamics of solar flares, the interiors of stars, or the magnetic fields threading galaxies. From a computational perspective, tensors have also become central to modern technology. Machine learning, particularly in the field of deep neural networks, relies heavily on tensor operations. Frameworks like TensorFlow and PyTorch take their names from this fact. In this context, tensors are not fields in spacetime, but multi-dimensional arrays of numbers, manipulated through linear algebra to extract patterns from data. Though this application differs from physics, it reflects the same underlying principle. Tensors organize complex, multi-directional relationships in a way that can be computed and generalized. One more remarkable role of tensors is in the propagation of gravitational waves. These ripples in spacetime, predicted by Einstein and confirmed a century later, are described by perturbations of the metric tensor. As waves pass through, they distort distances in orthogonal directions, stretching and squeezing space itself. This effect is minuscule, smaller than the width of a proton over kilometers of separation, yet detectable thanks to the precision of interferometers like LIGO. Here again, tensors are not an abstract tool, but the very description of physical motion in the universe. The beauty of tensors in motion lies in their adaptability. In every field, they condense complexity into structure, turning what might seem like a chaotic interplay of forces into a system that can be analyzed, predicted, and understood. They are the bridge between physical intuition and mathematical precision, the vessels through which the laws of nature express themselves in consistent form. And so, at the quiet edge of this chapter, an existential thought surfaces. When we say that tensors describe forces and fields, we are not merely speaking about abstract mathematics. We are describing the patterns of interaction that hold reality together. The stresses that shape materials, the fields that carry light, the curvatures that guide stars. In their motion, tensors reveal that the universe is not disorderly but deeply structured, woven together by relationships that can be expressed, understood, and perhaps even predicted. It is as if the cosmos itself insists on being readable, offering us a grammar of forces written not in words but in tensor. Chapter 7. Tensors and the Shape of the Universe. When we speak of the universe as a whole, one of the deepest questions we can ask is about its shape. This does not mean the shape we see on maps or the outlines of galaxies against the night sky. Instead, it refers to the geometry of spacetime itself, the grand architecture in which all cosmic structures are embedded. Is the universe flat, stretching endlessly without curvature? Is it positively curved, like the surface of a sphere, finite but without boundary? Or is it negatively curved, like a saddle, extending without limit in every direction? To answer these questions, physicists turn not to intuition or simple observation, but to tensors, the mathematical language that encodes geometry at the most fundamental level. The story begins with the realization that geometry is not static, but dynamic. In the early 20th century, Einstein's general relativity redefined gravity as the curvature of spacetime. The fabric of the cosmos bends under the influence of matter and energy, and that bending determines how objects move. But Einstein's equations do more than describe local curvature around stars and planets. They can also be applied to the universe as a whole. If spacetime itself is a manifold described by a metric tensor, then the global properties of that tensor determine the cosmic shape. The key object here is the metric tensor. It tells us how to measure distances and angles everywhere in spacetime. From it, one can derive curvature tensors that describe how spacetime bends. If the curvature vanishes everywhere, the universe is flat. If the curvature is positive, the universe is closed, curving back on itself. If the curvature is negative, the universe is open, expanding forever in a saddle-like geometry. In this way, the tensor formalism provides the rigorous framework to define what we even mean by the shape of the universe. Early on, Einstein himself believed the universe must be static. He imagined a cosmos where stars remained roughly fixed relative to one another, neither expanding nor contracting. But his field equations did not naturally allow for this. They suggested that the universe should either expand or contract, depending on its contents. To force a static solution, Einstein introduced the cosmological constant, a term that effectively acted as a repulsive force to counterbalance gravity. Decades later, when Edwin Hubble discovered that galaxies are receding from one another, Einstein reportedly called his cosmological constant his greatest blunder. Yet that same term has returned in modern cosmology as a way to describe dark energy, the mysterious driver of cosmic acceleration. To model the large-scale universe, physicists rely on a solution to Einstein's equations known as the Friedmann-Lemaitre-Robertson-Walker metric, or FLRW metric for short. This solution assumes that the universe is homogeneous and isotropic on large scales. That is, it looks the same everywhere and in every direction. While galaxies form clusters and filaments, the universe as a whole, when viewed across billions of light-years, appears smooth. Under these assumptions, the FLRW metric reduces the complexity of Einstein's equations to a manageable form, allowing cosmologists to explore the possible shapes of the universe. The results fall into three broad categories: flat, closed, and open universes. A flat universe corresponds to zero spatial curvature. Here, parallel lines remain parallel, and the rules of Euclidean geometry hold true on cosmic scales. A closed universe has positive curvature, like the surface of a sphere. In such a universe, if you travel far enough in one direction, you could in principle return to your starting point. It is finite but unbounded, containing only a limited amount of space. An open universe has negative curvature, like a saddle. Parallel lines diverge, and the geometry is hyperbolic. Such a universe is infinite, expanding forever, with no possibility of looping back to the same location. Which of these options describes our cosmos is an empirical question, and to answer it, physicists look to observations of the cosmic microwave background radiation. This faint afterglow of the Big Bang carries within it tiny fluctuations, imprints of the universe's earliest structure. By measuring the size of these fluctuations on the sky, scientists can infer the geometry of spacetime. The Wilkinson Microwave Anisotropy Probe, WMAP, and later the Planck satellite have provided high-precision maps of the microwave background, and the results are striking. The universe is very nearly flat, with only tiny deviations from zero curvature. Flatness, however, raises questions of its own. Why should the universe be so finely balanced between the extremes of positive and negative curvature? This puzzle is addressed by the theory of cosmic inflation, which proposes that in the earliest moments after the Big Bang, the universe underwent a rapid exponential expansion. Inflation would have stretched any initial curvature to near flatness, just as the surface of a balloon looks flatter the larger it becomes. Again, the tensor formalism is central. The dynamics of inflation are described by fields and their energy-momentum tensors, feeding into Einstein's equations to drive expansion. The shape of the universe is not only about curvature but also about its ultimate fate. In a closed universe dominated by matter, expansion might one day halt and reverse, leading to a big crunch. In an open universe, expansion continues forever, thinning out galaxies until the cosmos becomes cold and dark. In a flat universe, the fate depends on the balance of matter, radiation, and dark energy. Current observations suggest that dark energy dominates, driving accelerated expansion. This points toward a future where the universe grows emptier and colder, a heat death in which stars burn out, galaxies drift apart, and even black holes eventually evaporate. Tensors enter this picture not only as abstract mathematics, but as the tools that connect theory to observation. The stress-energy tensor describes the contents of the universe: radiation, baryonic matter, dark matter, and dark energy. The Einstein tensor describes the curvature of spacetime. Their interplay in Einstein's equations yields the Friedmann equations, simplified versions that govern cosmic expansion. Every measurement of cosmic distances, galaxy surveys, and background radiation is interpreted through this tensorial framework. Without it, our discussions of cosmic shape would be hand-waving metaphors. With it, they become precise scientific statements. One of the most intriguing implications of this framework is that the universe might not be globally simple. While the FLRW metric assumes homogeneity, reality might contain subtler structures. There is speculation that the universe could have a non-trivial topology, meaning it could be finite but connected in complex ways. In such a universe, light traveling long distances might loop around, producing repeated patterns in the cosmic microwave background. Searches for such signatures continue, but so far none has been definitively observed. Still, the possibility underscores how tensors not only describe local curvature, but allow us to imagine global structures far beyond everyday intuition. The use of tensors in cosmology also reveals the interconnectedness of scales. The same formalism that describes the curvature around a single star also governs the shape of the entire universe. Local and global geometry are linked by the same equations. This unity is one of the triumphs of general relativity, a testament to the power of tensors as the universal descriptors of reality. There are, however, limits. General relativity does not account for quantum effects, and in the earliest moments of the universe, when densities and temperatures were extreme, quantum mechanics must have played a dominant role. A complete description of the universe's shape will require a theory of quantum gravity, uniting tensors with the probabilistic rules of quantum fields. Whether string theory, loop quantum gravity, or some other framework provides the answer remains an open question. For now, the tensorial description of spacetime remains our most reliable guide, consistent with every observation we have made. To step back from the technical details, the question of the universe's shape is also a philosophical one. What does it mean to live in a flat universe, an infinite expanse without boundary? What does it mean if the cosmos is curved back on itself, finite but unending? These are not just mathematical distinctions, but reflections on our place in reality. The tools of tensors and relativity allow us to measure, calculate, and predict, but they also invite us to wonder. And here lies the quiet, existential thought at the end of this chapter. The shape of the universe is not chosen by us, nor is it something we can alter. It is written into the fabric of space-time itself, a geometry that existed long before life arose to ask the question. Through tensors, we glimpse this hidden architecture. They reveal that we are not separate from the universe's shape, but part of it. Living beings carried within its curvature, moving along geodesics set by the cosmos itself. To know the universe's shape is, in some small way, to know ourselves, patterns of matter tracing the vast geometry of existence. Chapter 8. Quantum Fields and Tensors, the Invisible Machinery. When physicists look deeper into the universe, they find that matter and forces are not built from solid, indivisible pieces, but from something more abstract. The foundation of modern physics is not particles bouncing like billiard balls in empty space, but fields extending across all of reality. Electrons, photons, quarks, and gluons are not isolated dots. They are localized excitations of underlying quantum fields. These fields fill every region of space-time, fluctuating incessantly, interacting with one another, and giving rise to the phenomena we measure in the laboratory and observe in the sky. To describe this invisible machinery in a way that remains valid for all observers, the mathematics must encode both geometry and symmetry. Tensors provide that language. They allow us to write the laws so that their content does not depend on arbitrary coordinate choices, and so that the same physical statement appears with the same form to every inertial observer. Even before quantum theory, fields were central to physics. A gravitational field described how mass influences the motion of other masses. An electric field described how charge influences other charges. Those classical fields could often be treated as scalar or vector quantities, and their dynamics were expressed by differential equations tied to the geometry of flat space and absolute time. Quantum theory transformed this picture. Particles are no longer independent entities sitting in pre-existing fields. Rather, each particle is a quantized excitation of a corresponding field. The electron field supports excitations we call electrons and positrons. The electromagnetic field supports excitations we call photons. The quark fields, together with the gluon field, account for the interior of protons and neutrons. The Higgs field pervades the vacuum and shapes the masses of other excitations. Because these fields live in spacetime and must respect the principles of relativity, their mathematical description must tell us precisely how their components transform under changes of frame. That is where tensors enter decisively. Relativity insists that the laws of nature look the same to all observers moving at constant velocities relative to one another. This requirement forces physical equations to be covariant. If we change coordinates by a transformation that mixes space and time, the form of the equations must remain intact. Fields therefore come with transformation rules. A scalar field is invariant. Its value at a point does not depend on the orientation or motion of the observer. A vector field has components that rotate and boost like arrows in spacetime. Spinor fields transform in subtler ways that reflect the geometry of spacetime at the level of the Lorentz group. Higher-rank tensor fields carry multiple indices and encode relationships among directions simultaneously. Writing the laws with tensors ensures that, although components change when we change coordinates, the underlying object, the physical field, remains the same. Electromagnetism provides a clean and famous example. 19th century physics already knew that changing electric fields create magnetic fields, and that changing magnetic fields create electric fields. But only with relativity did it become clear that electricity and magnetism are two aspects of a single entity. Expressing the electric and magnetic fields as components of one rank 2 tensor makes their unity explicit. A boost to a new frame mixes those components. What one observer calls a pure electric field may appear to another as a blend of electric and magnetic fields. Yet the tensor as a whole captures invariant information, and the equations governing it look the same in every inertial frame. The stress carried by the electromagnetic field, its energy density, momentum flux, and pressure, can also be assembled into a tensor, allowing us to track how light pushes on matter and how radiation transports energy through space. Non-abelian gauge theories reveal an even deeper role for tensors. Quantum chromodynamics describes quarks interacting through gluon fields that live in an abstract color space. The fields transform under a symmetry more intricate than that of electromagnetism, and the quantities that measure their curvature play the same conceptual role as electromagnetic field strengths, while carrying additional indices that track color. Because the symmetry is non-abelian, the gauge fields interact with themselves, leading to phenomena such as confinement, in which quarks are permanently bound into hadrons. The equations that encode how these fields evolve and interact are written with tensor objects that carry both spacetime and internal indices, and their structure guarantees the consistency of the theory under local symmetry transformations at every point in spacetime. Quantum field theory adds another layer through the principle of locality. Influences propagate no faster than light, and fields at points separated by space-like intervals behave in ways that preserve causality. Those constraints are geometric. Light cones, intervals, and invariant separations are determined by the metric of spacetime. Tensors express these relationships without reference to any particular coordinates. Correlation functions, which quantify how excitations at one point are related to excitations at another, are built to respect these causal structures. They vanish or acquire specific analytic properties when points are space-like separated. The entire calculational framework of quantum fields, from propagators to scattering amplitudes, rests on tensor quantities whose transformation rules preserve the relativistic skeleton of the theory. Symmetry does more than improve aesthetics. It has consequences that can be measured. Continuous symmetries imply conserved quantities, and the object that packages energy density, momentum density, and their fluxes is the stress-energy tensor. In classical field theory, this tensor can be obtained by examining how the action responds to gentle distortions of spacetime. In quantum theory, it becomes an operator. Its expectation values tell us how much energy the vacuum carries in a given region, how momentum flows through a system, and how pressure is exerted by radiation or matter. The source term in Einstein's field equations is precisely this tensor. So in a semi-classical setting, where quantum fields live on a background geometry, their energy and pressure curve spacetime. Even without writing formulas, the conceptual point is straightforward. The stress-energy tensor is the bridge between quantum fields and gravitational geometry. The quantum vacuum is not empty. Even in the lowest energy state, fields fluctuate. Pairs of virtual excitations flicker into and out of existence, too briefly to be directly observed, yet their integrated influence can be measured. When two uncharged metal plates are placed close together, the allowed vacuum fluctuations between them differ from those outside, shifting the energy of the ground state and producing a small but definite force drawing the plates together. Subtle shifts in atomic spectra, such as the Lamb shift in hydrogen, and the exquisite agreement between theory and experiment for the electron's magnetic moment, arise from vacuum fluctuations and their tensorially constrained interactions with matter. These examples are not curiosities. They are precision tests that the invisible machinery, expressed through tensor equations, is real. The Higgs mechanism illustrates how one field can reshape the behavior of others. The Higgs field acquires a uniform value throughout space, and in doing so, it changes which excitations are massless and which are not. Gauge bosons associated with the weak interaction become massive, while the photon remains massless. Fermions obtain masses through their couplings to the Higgs. The underlying electroweak symmetry is hidden rather than destroyed, and the tensor equations that expressed it remain valid when rewritten in terms of the fields appropriate to the low-energy world. When experiments at the Large Hadron Collider observed a new boson with the properties predicted for the Higgs, it was an empirical confirmation that a scalar field with specific transformation properties really does permeate the vacuum. Condensed matter physics provides a different arena where tensors organize complex behavior. The conductivity of a crystal is not generally a single number. It is a tensor that captures how current responds to an applied electric field along different crystallographic directions. The same is true for dielectric permittivity, magnetic susceptibility, and elastic stiffness. In topological phases of matter, quantities such as Berry curvature play roles analogous to field strengths in momentum space, and the responses of these systems, quantized conductance in the quantum Hall effect, for example, are encoded by geometric tensors insensitive to microscopic details. Although these materials live at low energies compared with particle physics, the mathematical structures recur. Symmetry dictates allowed responses, geometry shapes dynamics, and tensors collect the relevant information into coordinate-independent statements. When quantum fields are placed in curved spacetime, new phenomena appear that link quantum theory to gravity. An observer who accelerates uniformly through what another observer calls empty space perceives a bath of particles with a temperature set by the acceleration. The effect arises because the notion of a particle depends on how an observer slices spacetime into time and space, and that slicing is geometric. Near a black hole, quantum fields produce thermal radiation with a temperature proportional to the surface gravity, implying that black holes are not perfectly black but slowly evaporate. These results, though derived without writing down explicit formulas here, use the same tensorial concepts: fields with well-defined transformation properties, stress energy determining back reaction, and curvature controlling the propagation and mixing of modes. The standard model of particle physics assembles the known non-gravitational interactions into a single framework that has been tested to extraordinary precision. It is built by placing fields into representations of a symmetry group and allowing interactions consistent with local invariance, causality, and unitarity. Fermion fields carry spinorial indices that reflect their half-integer spin. Gauge fields carry both spacetime and internal indices. Scalar fields provide the simplest transformation behavior and can condense, as the Higgs does, to reorganize the spectrum. The remarkable breadth of phenomena explained by this structure, from the stability of atoms to the decays of heavy quarks, rests on the fact that tensor equations written to respect symmetry and relativity leave very little freedom for the dynamics to go wrong. Not every classical symmetry survives quantization intact. Some are spoiled by quantum effects known as anomalies, which reveal themselves when a conservation law that seems exact at the classical level fails once fluctuations are taken into account. The currents that diagnose these failures are tensorial, and their divergences expose the anomaly. Demanding that dangerous anomalies cancel is not a matter of taste. It is required for consistency. Without that cancellation, probabilities could fail to add to one, or local gauge symmetry could not be implemented globally. Remarkably, the requirement that anomalies cancel constrains the arrangement of fermion species and their charges, providing a logical thread running through the particle content we observe. On the computational side, tensor structures have inspired powerful numerical methods. Lattice gauge theory replaces continuous spacetime with a discrete grid and evaluates averages by sampling many field configurations, maintaining gauge invariance exactly on the lattice and assembling observables from long chains of tensor contractions. With sufficient computing power, hadron masses, form factors, and the thermodynamics of hot, dense matter can be predicted from first principles. In low-dimensional many-body systems, tensor network methods approximate highly entangled quantum states with structured families of tensors connected in specified patterns. These networks capture ground states and low-energy excitations efficiently, turning abstract ideas about entanglement and geometry into concrete algorithms that match experiments on cold atoms and quantum magnets. Experiments continue to probe the places where these ideas are most delicate. Measurements of the electron's magnetic moment agree with quantum electrodynamics to more than 10 significant digits, an achievement that relies on tensorially consistent bookkeeping of every contribution. Neutrino oscillations show that the fields associated with different neutrino flavors mix as they propagate. The mixing is encoded by unitary transformations that preserve vector and tensor currents and can be observed through deficits and appearances of particular flavors over long baselines. High-energy collisions at the Large Hadron Collider create showers of particles whose distributions reflect the tensorial couplings among quarks, gluons, and electroweak bosons. Detailed comparisons between data and theory test whether any deviation from the standard model lurks in the tails of those distributions. At the frontiers, researchers try to connect quantum fields to geometry in even more direct ways. Ideas from holography suggest that certain quantum field theories are equivalent to gravitational theories in higher dimensional curved spaces. In that correspondence, patterns of entanglement in the field theory are related to geometric surfaces in the gravitational description, and correlation functions computed on the field theory boundary correspond to the propagation of fields through the gravitational bulk. While still a developing program, it treats tensors as the connective tissue on both sides. Correlation functions assembled from tensor operators map to geometric quantities built from curvature tensors and metrics. The proposal is audacious, but it is consistent with a theme that has already guided physics for a century. Where there is symmetry and geometry, tensors will provide the grammar. Outside high-energy physics, quantum fields and their tensor descriptions illuminate ultra-cold atomic gases, unconventional superconductors, and materials whose electrons behave as though they are relativistic particles. These platforms let us simulate aspects of quantum field theory in the laboratory, tuning couplings and dimensionalities in ways that would be impossible in the early universe or at colliders. Vortices in superfluids mimic cosmic strings in a controlled setting. Dirac and Weil semimetals realize quasi-particles with linear dispersion relations, and their responses to strain or magnetic fields can be expressed naturally through effective tensor fields. Spin liquids exhibit emergent gauge fields whose dynamics mirror those of high-energy theories, blurring the line between condensed matter and particle physics, and highlighting again that the same mathematical language spans widely separated energy scales. It is important to remember that the tensor is not the physics, it is the representation. Its power comes from the demand that laws be the same for every observer and every allowed transformation. Tensors fulfill that demand by letting equations stand independent of coordinates, while quantum fields fulfill it by distributing degrees of freedom across space and time in a way that marries locality with symmetry. Together, they produce a framework that is predictive and falsifiable. The heavy machinery of indices and transformation rules is not pedantry. It is the means by which we prevent ourselves from confusing artifacts of description with properties of the world. The invisible machinery is therefore less mysterious than it first appears, though no less profound. We do not see quantum fields directly. We infer them from patterns in data that align with tensor-based predictions. We do not handle the stress-energy tensor with our hands. We read it from how detectors warm or cool, from how beams deflect, from how clocks tick in different gravitational potentials. The success of these inferences is the test that keeps the abstraction honest. Every time a calculation agrees with an experiment to astonishing precision, we gain confidence that the language of fields and tensors is not merely convenient but faithful. In the quiet that follows the technical story, a thought settles. What seems solid is a play of fields, and what seems complicated is organized by symmetry into a language that does not change from place to place or frame to frame. We are small excitations in those fields, brief ripples that think and ask questions. Tensors do not make the universe, they describe it with a fidelity that feels like revelation. In learning to read them, we learn to read ourselves as parts of the same invisible machinery. Chapter 9, Beyond Physics, Tensors in Technology and AI. Tensors emerged from mathematics and found their first decisive role in physics, where they became the indispensable framework for general relativity, electromagnetism, and quantum field theory. Yet their reach has expanded far beyond the confines of fundamental science. Today, tensors are central not only to our understanding of the universe, but also to the technologies we use in daily life. They power modern computation, underlie advances in artificial intelligence, and structure data in ways that allow machines to recognize patterns, translate languages, and even generate human-like creativity. What began as an abstract language of geometry has become a practical tool shaping the digital age. At its core, a tensor is a structured way of organizing numbers. A scalar is a single number. A vector is a sequence of numbers with directionality, and a matrix is a two-dimensional arrangement of numbers that can transform vectors. A tensor generalizes all of these concepts to higher dimensions. This generalization might seem abstract, but it is exactly what is required when dealing with data that naturally exists in multiple dimensions. For example, a grayscale image can be represented as a two-dimensional array of intensity values. A color image requires three dimensions: height, width, and color channels. A video introduces a fourth: time. Audio signals, spatial sensor readings, and medical imaging scans can all be represented naturally as tensors. The ability to organize and manipulate such data consistently is why tensors have become the backbone of machine learning. Modern artificial intelligence relies on neural networks, computational architectures inspired loosely by the organization of neurons in biological brains. These networks are built from layers of operations that process data step by step. At each stage, data is represented as a tensor, transformed through matrix multiplications, nonlinear activations, and convolutions into new tensors that carry progressively more abstract representations. A photograph of a face, for instance, might begin as raw pixel intensities. Early layers detect edges and textures. Deeper layers assemble these into features like eyes, noses, or mouths. At the highest levels, the network encodes abstract concepts such as identity or emotion. Throughout this process, the tensor is the vessel carrying information forward, and tensor operations are the gears that drive the transformations. The efficiency of these operations is crucial. Neural networks contain millions or even billions of parameters, adjustable weights that determine how inputs are transformed. Training them requires vast amounts of data and computation. The linear algebra operations that update these parameters are tensor operations, and hardware accelerators like graphics processing units, GPUs, or tensor processing units, TPUs, are specifically designed to perform them quickly. What once required months of computation on conventional hardware can now be achieved in days or hours thanks to optimized tensor arithmetic. The very names of the most widely used software frameworks for machine learning, TensorFlow and PyTorch, reflect this centrality. Convolutional neural networks, which revolutionized image recognition, rely on tensor operations that slide small filters across larger arrays of data. Each convolution is a tensor contraction, summing over specific indices to produce new arrays. Recurrent networks designed for sequential data like speech or text propagate information through tensors that carry memory from one step to the next. Transformer architectures, which now dominate natural language processing and generative AI, depend on tensor manipulations of attention scores, aligning information across sequences in ways that capture long-range dependencies. In every case, the consistency of tensor mathematics ensures that these operations can be composed reliably, scaled efficiently, and generalized across tasks. The applications extend far beyond research laboratories. When a smartphone recognizes a face to unlock its screen, it performs tensor computations on the captured image. When an online translator converts a sentence from one language to another, tensors carry the representation of words through a deep network that encodes meaning. When medical imaging algorithms detect subtle patterns in scans that might indicate early disease, they do so by analyzing tensor-structured data through trained networks. The invisible calculations that underlie these tasks are tensorial in nature, organized and accelerated by the same mathematics that describes spacetime curvature and quantum fields. The connection between physics and AI is not merely metaphorical. Techniques developed in physics for handling tensors have found direct application in computation. In condensed matter physics, tensor network methods approximate the states of many-body systems by structuring entanglement efficiently. These same methods inspire algorithms in machine learning, where they are used to compress neural networks, reduce redundancy, and improve interpretability. Conversely, machine learning itself is now applied to physics, with AI models trained to recognize patterns in particle collisions, gravitational wave signals, or astronomical surveys. The common denominator is the tensor, serving as the bridge between physical systems and computational tools. Tensors also enable multimodal learning, where data of different types is combined. Human experience is not confined to a single modality. We see, hear, touch, and move in a world that presents information across many channels. To build AI systems that approach human-like understanding, different forms of data must be integrated. A self-driving car, for example, combines camera images, radar signals, LiDAR maps, and GPS coordinates. Each of these is structured as a tensor, and their fusion is carried out by tensor operations that preserve the integrity of the data while enabling joint analysis. This capacity to integrate across modalities is one reason tensors are viewed as the natural data structures of intelligence. The influence of tensor mathematics extends even further into optimization and control. Training a neural network is an exercise in adjusting millions of tensor parameters so that predictions align with data. Gradient descent, the iterative process used to achieve this, relies on tensor calculus to compute derivatives efficiently. Backpropagation, the algorithm that propagates error signals backward through the network to update parameters, is essentially a chain of tensor transformations. Without tensor calculus, the modern revolution in deep learning would not have been computationally feasible. Beyond artificial intelligence, tensors structure data in scientific computing more generally. In climate modeling, tensors represent variables across three-dimensional grids of the atmosphere and oceans, evolving over time. In finance, tensors encode correlations across markets, assets, and time horizons. In medicine, tensors organize genetic information, biochemical networks, and the progression of disease states. In each domain, the multidimensional nature of the data demands tensorial representation. By extending mathematics beyond the limitations of vectors and matrices, tensors provide the scaffolding required to analyze the complexity of real-world systems. The rise of quantum computing has introduced yet another frontier where tensors play a central role. Quantum states of many particles are described by wave functions that can be represented as high-ranked tensors. The exponential growth of possible states with the number of particles makes direct storage impossible, but clever tensor decompositions, breaking a large tensor into networks of smaller ones, allow simulations to proceed far beyond naive limits. Quantum algorithms themselves often involve tensor transformations of amplitudes, and efforts to design quantum machine learning architectures are built upon this shared foundation. Here, as in classical computing, tensors provide both the representation of information and the language for its manipulation. It is remarkable to consider how a concept developed for geometry in the 19th century has become indispensable for digital technology in the 21st. The same structures that allow us to describe the curvature of the cosmos now allow machines to identify objects in photographs or compose fluent text. This is not a coincidence. Both in physics and in computation, the challenge is to represent relationships that span multiple dimensions, to encode interactions that cannot be captured by single numbers or even by simple arrays. Tensors are the most natural way to do this, ensuring that the rules of transformation remain consistent across changes of perspective, whether those perspectives are coordinate systems in spacetime or layers in a neural network. The universality of tensors also highlights a deeper theme, that mathematics developed in one context can find unexpected application in another. Ricci Curbastro and Levi Civita, when developing tensor calculus, were motivated by geometry. They could not have foreseen GPUs, machine learning, or self-driving cars. Einstein, in applying their language to relativity, could not have imagined that the same structures would someday underlie artificial intelligence. Yet this is the nature of mathematics. Once discovered, its truths are timeless, waiting for new contexts to reveal their relevance. And so, as this chapter closes, a gentle existential reflection arises. The same mathematical objects that allow us to describe stars bending light and the expansion of the universe now structure the algorithms that interpret our words and images. Tensors are the invisible threads connecting the deepest laws of nature with the everyday technologies of human life. They remind us that knowledge is not compartmentalized but woven, and that the language of the cosmos is also the language of our machines. To understand tensors is to glimpse the unity of understanding itself, the recognition that the patterns that govern galaxies also govern data, and that in both cases, the grammar of reality is written in the quiet, enduring form of tensors. Chapter 10. The Poetry of Tensors, Why They Explain Reality. By the time we reach the end of the story of tensors, it becomes difficult not to see them everywhere. What began as a way to keep track of how quantities change under rotations and relabelings has become the language that connects measurement with meaning across the sciences. Tensors did not earn their prominence because they are ornate. They earned it because they enforce objectivity. A physical statement should not depend on the coordinates we choose, the units we prefer, or the frame from which we look. The demand that laws be independent of description is not a stylistic preference, but a criterion for truth, and tensors are the mathematical way of meeting that criterion. Calling a tensor a multi-directional quantity touches only the surface. The deeper point is that a tensor is defined by how it transforms. Two observers may decompose the same field into different components, yet they agree on the underlying object because its components change in a prescribed way when axes rotate or frames are boosted. That prescription is not bookkeeping trivia. It is the bridge that allows results from different laboratories to be compared. Scalars give us facts that everyone shares without translation. Vectors add direction, and their components shift predictably with the frame. Higher-ranked tensors encode relationships among multiple directions at once. The power of the framework is that the object exists independently of any particular decomposition, so that what is measured is not an artifact of perspective, General covariance sharpens what is at stake. In a relativistic world, there is no global grid stamped onto spacetime, no preferred family of rulers and clocks. Laws must make sense on any smooth manifold with any coordinate chart. The metric tensor, which tells us how to measure intervals, does more than assign lengths. It organizes causal structure by distinguishing time-like, light-like, and space-like separations. Curvature tensors go further, telling us how nearby geodesics converge or shear and how parallel transport around a loop fails to return a vector to itself. None of this depends on drawing a picture in an embedding space. Curvature is intrinsic, and tensors are the intrinsic way to speak about it. Locality and causality enter through the same doorway. Field equations relate values and rates of change within small neighborhoods. Whether a disturbance propagates with finite speed, whether an initial value problem is well posed, and whether waves disperse or focus, all depend on the tensor that encodes the causal cones. The stress-energy tensor organizes what can supply or drain energy, and its conservation expresses a balance that holds in any coordinates. Energy conditions, tensor inequalities that restrict how stress and pressure can behave, translate intuitive physical requirements into coordinate-free constraints. When such conditions hold, we obtain global statements. Families of geodesics focus in predictable ways, horizons form under specified circumstances, and singularities cannot be avoided if certain patterns persist. The different register of the same language appears in the calculus of differential forms, which are themselves tensors tuned to measure oriented fluxes. When we integrate a 2-form over a surface or a 3-form over a volume, the result is independent of how that surface or volume is parametrized. This is why the most economical statement of classical electromagnetism packages the electromagnetic field as a 2-form and its source as a 3-form. The identities that relate their exterior derivatives are simply geometric statements about boundaries and orientation. The Hodge dual, defined by the metric, turns forms of one degree into forms of a complementary degree and lets flux statements become density statements. The entire structure is tensorial, and its invariance is what makes the same equations valid for antennas in a lab and for magnetic fields threading galaxies. Science requires measurement, so a universal language must connect to laboratory procedure. The metric tells us how to calibrate rods and clocks and how to synchronize them within the limits set by causality. The stress tensor tells us how to infer internal forces from boundary tractions, how to interpret pressure and shear in complex flows, and how to transport those readings between frames that are moving relative to one another. Constitutive tensors, which relate fields of cause to fields of response, say how particular materials behave. They encode anisotropy, memory effects, and nonlinearities. The very possibility of designing instruments that read the same in different orientations or at different speeds relies on these tensorial rules, because they say which combinations of measurements are frame features and which are features of the world. Symmetry deepens the explanatory power. When a system possesses a continuous symmetry, there is a corresponding conservation law. The currents that encode these laws are tensorial, and their vanishing divergence is a physical statement. Energy and momentum are transferred but not destroyed, and electric charge accumulates only by inflow. Such linkages are not slogans pasted onto equations. They are structural facts that explain why a law has the shape it does. Because the statements are tensorial, they retain their force no matter how we slice spacetime into space and time, or how we label the axes on a diagram. In this sense, The mathematics is not a layer of polish over physics. It is the form in which the physics can be made precise. Constitutive relations compose another verse in the same poem. Fundamental equations are not enough to make predictions. We must also specify how particular media respond. Those responses are often anisotropic and sometimes nonlinear or history-dependent. The conductivity of a crystal depends on direction. The stiffness of a laminate varies across axes set by its microstructure. The viscous stresses in a complex fluid reflect not only the instantaneous rate of strain, but the memory of past deformations. In each case, the response is a tensor that encodes the link between cause and effect. And the structure of that tensor is constrained by symmetry and by positivity requirements that exclude unphysical behavior. Principal axes arise because symmetric tensors can be diagonalized, allowing us to align coordinates with the material's natural directions without changing the underlying object. This is not an algebraic trick. It is the mathematical expression of how nature prefers to respond. Across scales, tensors help us track what survives coarse graining. Microscopic detail washes out when we pass to macroscopic descriptions, but certain structures persist because they are protected by symmetry or by conservation. Hydrodynamics, for instance, emerges as a universal long-wavelength theory in which densities, currents, and stresses evolve according to balance laws. Even when the constituents differ, atoms in a gas, spins in a magnet, vehicles in traffic, the same patterns reappear. The renormalization group formalizes this endurance, showing how parameters flow as we zoom out and why disparate systems land on the same families of effective tensors. Critical phenomena display this vividly. Near a phase transition, correlation lengths grow, and the macroscopic response tensors acquire scaling forms that ignore most microscopic detail. Tensors also delineate the limits of predictability. Energy conditions restrict how exotic matter can be if we wish to avoid violations of causality or thermodynamics. When they hold, global theorems tie local inequalities to cosmic architecture. Conversely, when carefully controlled violations occur, as they can in quantum fields with locally negative energy densities, tensor statements remain the way we register the exception and calculate its consequences. The point is not that the universe is a slave to inequality signs written in indices, but that these succinct, coordinate-free statements carve the logical space of possibilities into regions where certain behaviors are mandatory, forbidden, or allowed only fleetingly. If tensors feel ubiquitous, it is because the same need recurs, to keep track not just of magnitudes but of relations among directions, to encode laws so they are frame indifferent, and to link those laws to measurable operations. The symplectic form in Hamiltonian mechanics, a closed two-form on phase space, instructs trajectories how to thread the sea of possibilities. It guarantees that volumes in phase space are preserved under time evolution and that canonical transformations leave the physics intact. Here, as in spacetime geometry, the content of the theory is expressed in a tensor whose invariance keeps dynamics honest over long times and across alternative sets of variables. Liouville's theorem, adiabatic invariance, and the geometric structure of integrable systems are all tensorial at their core. The language reaches into places that, at first, look far from geometry. In irreversible thermodynamics, linear response close to equilibrium is controlled by transport tensors, whose symmetries reflect microscopic reversibility. Phenomena as diverse as heat conduction, diffusion, and thermoelectric coupling are knitted together by reciprocity relations that identify conjugate flows and forces. The positivity of entropy production places inequality constraints on these tensors, delimiting the space of allowed material behaviors. In seismology, the moment tensor encapsulates how an earthquake source deforms the surrounding rock, allowing geophysicists to infer fault orientation and slip from the pattern of waves at distant stations. In medical imaging, diffusion tensors describe how water spreads anisotropically through tissue, making white matter tracts visible to non-invasive scans. In each case, tensors marshal complex directional dependencies into compact statements that travel intact from model to measurement. There is a bridge between matter and information as well. The same discipline of writing coordinate-free statements in physics has a computational parallel: data structures and algorithms that do not depend on arbitrary choices. When an algorithm processes images, speech, or multi-sensor streams, the intermediate representations are tensors, and the rules for manipulating them preserve content while discarding accidental features, such as where an object falls on a grid or how a sentence is padded in memory. Although that story belongs to technology rather than fundamental physics, it rhymes with the same theme. To say anything reliable about a complex system, one must first decide which features should survive a change of description. Tensors are the grammar for writing that decision down. One might worry that talk of poetry risks romanticizing what should be austere. But the poetry here is not decoration. It is the recognition that certain patterns carry explanatory force because they are the only patterns consistent with broad constraints. Once we insist on locality, causality, symmetry, and operational meaning, a narrow path remains, and tensors pave it. Deviation has costs. A theory that abandons covariance will fail to be intersubjective. A theory that discards conservation will struggle to track flows through space and time. A theory that ignores constitutive structure will predict nothing specific. The demand that statements be tensorial is therefore not a taste for elegant symbols, but a filter that screens out confusions before they propagate. The tensor viewpoint also clarifies why different parts of physics hang together. Spin-half fields require local frames that can be rotated independently at each point. Tetrads provide that scaffolding, tying curvature to the behavior of matter with intrinsic angular momentum and allowing spinors to couple consistently to gravity. Gauge fields arise when we insist that only differences in certain internal phases are observable. The associated field strengths are tensors that measure the failure of those phases to return to themselves around loops. The classification of elementary excitations by how they transform, scalar, vector, spinor, and higher-rank generalizations, is a map of how matter and interactions fit together. The coherence across these domains is not an accident. It is a sign that tensors are the right backbone on which to hang laws. Even our numerical techniques bend to the same logic. Discretizations that respect the underlying tensor structure tend to produce stable and faithful simulations. Finite element spaces that exactly represent divergence-free fields preserve incompressibility without artificial sources or sinks. Structure-preserving integrators maintain symplectic areas so that long-time simulations of planetary systems do not drift unphysically. Lattice formulations keep gauge invariance exact at non-zero spacing, preventing spurious symmetry breaking and allowing controlled extrapolation to the continuum. When computations go wrong, the autopilot for diagnosing error is often a tensorial check. Does the discrete stress balance close? Does the discrete curvature behave covariantly? Does the computed flux satisfy the same integral identities as the continuum? None of this means that tensors are the final word. They are a language whose adequacy is judged by the breadth of phenomena it can describe and by the accuracy with which it predicts. Quantum gravity remains a frontier on which we do not yet know how to speak without contradiction. Yet even in speculative domains, the lesson persists. Proposals that respect the tensorial bones of locality, covariance, and symmetry have a fighting chance. Those that do not rarely endure. Effective field theories that integrate out heavy degrees of freedom and leave behind new coefficients multiplying tensor structures are our best way of organizing ignorance. If new interactions exist, they will enter as additional terms in the same grammar, constrained by the same symmetries and subject to the same demands for invariance. Perhaps the strongest reason to say that tensors explain reality is that they allow us to separate what can change with viewpoint from what cannot. Explanation, at its best, strips away the accidental and reveals the necessary. A statement that owes its validity to a particular coordinate choice is not an explanation. It is a recipe with hidden strings attached. A tensorial statement advertises its independence from those strings. That is why the same structures keep reappearing in new territories, from the curvature of spacetime to the response of materials, from the dynamics of phase space to the flow of information in algorithms. When ideas migrate and still fit, we recognize that we have touched something structural. There is humility in this perspective. Tensors do not tell us what the world must be. They tell us how to talk about what the world is, provided that it is coherent, local, and symmetric in the sense revealed by experiment. They are permissive enough to accommodate surprise, yet strict enough to rule out nonsense. When an observation refuses to fit, an anomaly that persists after every instrumental doubt is cleared, the tension is instructive. Either the constitutive tensors we assumed are incomplete, or the symmetries we believed were exact are only approximate, or the domain of the model has been exceeded. In all cases, the failure is legible because the language is legible. The grammar of tensors makes deviation stand out. In the quiet that follows the technical account, a human thought is allowed. The world could have been unintelligible. It could have refused to yield patterns that survive translation from one vantage to another. Yet it did not. It offered geometry, symmetry, and law, and in learning the language of tensors, we learn to listen. We remain finite creatures, and the universe remains larger than our descriptions. But the same invariants that hold galaxies together also hold our explanations together. If there is poetry here, it is the poetry of fidelity, a language whose rules do not bend with our perspective because they are copied from the structures of nature itself. My friend, thank you for spending this time with me tonight. I hope these thoughts about tensors and the shape of reality helped calm your mind and ease you towards sleep. If you're still awake and curious, there's another video waiting for you here that you might enjoy. And if your eyelids are already heavy, then I wish you sweet dreams among the stars. Until next time, rest well.